Let's take a look at the concept and practice of chemical equilibrium. This is in Chapter 15 of your Zumdahl book. I'm using some Prentice Hall slides that we've modified over the years. And the critical issue here is, see those two arrows. The one going from left to right you're familiar with. That's a forward reaction. But we're going to be looking also at the reverse reaction, the one going from right to left, and a specific set of conditions where those rates are equal. All right, we've encountered equilibria before. In the kinetics chapter, we ran into the reaction of nitrogen monoxide and bromine, and we said that ultimately we get NOBr out of it. But we said that this is a two-step reaction in which the first step is an equilibrium setup where the NO simply runs into the Br2 and forms what I call number 2. This, in turn, reacts with another molecule of NO in the slow step to give us NOBr. And this equilibrium step sets up the step 2, or the slow step, the rate determining step, so that the rate law has two NOs and a Br2 in it. We're not looking at that. That's a kinetics issue. What we'd like to know is about this reverse reaction. Now, if a chemical reaction is at equilibrium, then we are forming products as fast as the products breaking up to form reactants. That is, the rate of forward and reverse reaction are the same. That's the definition of equilibrium. If we then take the rate law for the forward reaction, K1, that's the K for the forward reaction, times NO times Br2, that's going to be equal to the rate of the reverse reaction, which is the K for the reverse reaction times the NOBr2. These rates are equal. If we then solve for the concentration or partial pressure of NOBr2, we simply divide both sides by the K of the reverse reaction, and this is what we get. If we then divide so that all the reactants and products are on one side, we divide by NO and Br2 both sides, we end up with this ratio of forward and reverse constants equal to the rate, the concentration of the product NOBr2 divided by the concentrations of the reactants NO and Br2. All right. Now, if you've done this the way I intended, you've already seen a little video of the nitrogen dioxide and dinitrogen tetroxide equilibrium. And you can see that in hot water, the NO2 predominates because it absorbs light, visible light, green light, and looks red. But the N2O4 does not absorb visible light, and so it's a lot paler. In fact, if you put the this one, the NO2 N2O4 equilibrium chamber, if you put it in dry ice, you'll get rid of the NO2 pretty much 100%. Only have the N2O4, we call that a dimer because you're shoving two NO2 molecules together. If you then warm it up to room temperature, or maybe this is ice water, you get some NO2 because some of the N2O4 breaks up. And if you put it in hot water, you get a lot more NO2 and a lot less N2O4. At each of these temperatures, a chemical equilibrium can set up, and it occurs when the reaction and its reverse proceed at the same rate. So here are three equilibrium situations, and as you know, the K's of the rate law, those change with temperature. Therefore, it looks like the equilibrium will change with temperature. And we'll see that as we move through this unit. All right. This is the rate of chemical reaction. If you start off down here with the rate of NO2, and you start off, NO2 is not reacting because there's none of it. Up here you've got all N2O4, and that's falling apart into NO2. So this reaction speeds up, this reaction slows down, and ultimately you get to an equilibrium where the rates of forward and reverse reaction are equal. As the system approaches equilibrium, both forward and reverse reactions are occurring. But at equilibrium, the forward and reverse reactions proceed at the same rate. They don't stop, even though it doesn't look like anything is happening, or it looks like nothing is happening. Indeed, the forward and reverse reactions are still occurring, but since they're going at the same rate, you can't see the change going on. Will the concentrations be equal? Well, that's a good question. If the rate of forward and reverse reactions equal, the question really is, are the K's forward and reverse the same? Probably not, which means the concentrations will almost certainly not be equal. Let's look more at that. The amount of each reactant and product remains constant. So here's your concentrations. And as you see, at this particular temperature, NO2 predominates. And the concentration doesn't change, even though the reaction forward and reverse is still proceeding. NO2 concentration is the same. N2O4 concentration doesn't change either, but they're not equal to each other. So, what do we have? The rates become equal at equilibrium. The concentrations become constant at equilibrium. Good. So, we depict equilibrium, both forward and reverse reactions occurring simultaneously. We depict that with a double arrow. N2O4 breaks up to form NO2. NO2 dimerizes to form N2O4. Now, we're going to compare or contrast the equilibrium with a steady state because they're often confused. You remember from biology the term homeostasis, I hope. It's the maintenance in a living organism of a constant internal milieu, even if the external environment changes. So you get hot, you sweat, the liquid in your perspiration evaporates. That's an endothermic reaction, so it takes heat from your body and turns the liquid into a vapor, and therefore cools your body down. There's another one, and there's many of these systems in your body. Your chemistry has to adjust to keep the CO2 level in your blood constant, and we'll learn a little more about that as this unit proceeds. Now, homeostasis mimics an equilibrium because concentrations are kept the same. But they don't stay the same by themselves. You have to constantly input energy and supply of nutrients and excrete waste. That's essential to keep those concentrations the same. Therefore, you have to have an open system for homeostasis. An equilibrium system, however, is a closed system. You saw the NO2, N2O4. Those tubes were closed. Yes, energy could come in and out, and that would change the equilibrium, but you didn't lose any NO2 or N2O4 because the tubes were sealed. So in an equilibrium system, nothing comes in, nothing goes out. Steady state and homeostasis. Homeostasis refers to the entire internal environment of the organism, or the cell, for instance. The term steady state can be restricted to describing specific mechanisms. But a cell is in homeostasis because every mechanism keeping it alive remains in a steady state. Okay, example. We won't be real detailed about this. There's an enzyme complex called sodium-potassium ATPase. It's also known as a sodium-potassium pump. You may have heard of it. You get energy from the hydrolysis of ATP to trade sodium ions in the cell for potassium ions that are outside the cell. And it maintains a constant internal concentration of potassium. So the potassium concentration is in a steady state, but it requires a constant production of ATP and movement across the cell membrane. Let's show you the picture here. This is outside the cell, this is inside the cell. The potassium pump takes potassium from outside the cell and brings it in, and takes sodium and pumps it out. And ATP drives that. Concentration of potassium ions outside the cell is 5 millimolar, so the enzyme needs ATP to pump from the low to high concentration of the potassium. Steady state characteristics then: the system is open. The rates at which species enter and leave is the same. Once established, the concentrations don't change. Changes in conditions can establish a new steady state. Like when you get cold, your muscles vibrate and therefore create heat to keep the body warm. Now, equilibrium and rate constant. So we're out of steady state. You won't be tested on that. Just wanted to make that clear. The rates of forward and reverse reaction in an equilibrium are the same. Does that make the K's equal? I think you probably can answer that question. No, not necessarily, from what you saw with the NO2 and 2O4. What will be the ratio of the rate forward to the rate reverse? Not the K's, but the actual rate. Answer: if it's at equilibrium, they have to be equal, therefore the ratio is always 1. Will that be the same as the ratio of the concentrations of product to reactant? Answer: of course not. If the temperature doesn't change, will the ratio of K's change? Well, we know that K is only dependent on temperature, therefore the ratio will not change. That brings us to equilibrium constant, which is our next video.